whatever we saw till now were stress-based algorithm. Okay, and now I'll not go into much deeper in strain-based algorithm because uh, typically all the vibrations, typically strain-based or low cycle fatigue comes when you have severe loading, severe temperature loading or bolt loading, bolt tightening. Bolt tightening, I would not say bolt tightening per se because that's not pulsating load. Okay, but you have something which is really causing your component stress to go into plastic zone repeatedly. Okay, so let's say truck cranking. So let's say when you start your vehicle, some component may undergo high strain. So may undergo a zone, I mean it may undergo into plastic zone, but how many times you will start and off your vehicle? Okay, those number of cycles may not be high. Okay, high as in high with respect to vibration number of cycles. Okay, so though it enters into plastic zone, it may enter into plastic zone for, let's say, few thousand instances, because you will turn on and off car maybe few thousand times, may not be million times or billion. Okay, but vibration cycles will definitely be million, because you have to undergo vibration, let's say if the frequency is 60 hertz, so 60 times per second. Okay, so you can assume the vibration number of cycles. But for engine cranking, the cycles may be in thousands. So for high strain or in plastic zone, the requirement may not be really, that they may not really expect survival for, infinite life or million cycles. They may expect survival for, let's say, 5,000 cycles. Okay. So typically these strain-based approaches, they deal in high stress, or rather I should say high strain zones. Okay, so here instead of really taking your stress for fatigue calculation, what you focus on is your plastic strain, which is it is strain range. Okay, which is delta epsilon p. Delta epsilon p is nothing but if you're let's say I plot this. Okay, notched. So the strain here at max loading and strain here as let's say min loading. Okay, so you have sigma min, I should not say negative or positive, it's sigma min, and so not sigma, sorry, epsilon min and epsilon max. Okay, so you calculate. Okay, at this notch specimen you will have high strain here, so you take epsilon minimum and epsilon maximum. Okay, you take delta of that, and then you kind of try to put that delta epsilon p into this equation. Now here, C is the fatigue ductility exponent. Now these are basically material constants. Okay, so these constants you get out of the different strain based or low cycle fatigue test done on material. So what you have to do from your simulation point is you have to take the delta of strain. Okay, and you have to use this Coffin-Manson, these curves, Coffin-Manson curves will be available in your fatigue handbooks. Okay, or maybe other material databases. So you have to take your epsilon, plastic epsilon range, and that you have to see how much, whatever range you have, let's say if you have range here, how much number of cycles you can sustain. Okay, so now, okay, so what Coffin-Manson said, Coffin-Manson was bothered about this plastic zone, but this is something which is coming from Baskin, because if you take this complete curve, what we saw SN curve, it is made of this this low cycle fatigue here, and it is also made of high cycle fatigue here. Okay, so if you have to really develop a generic fatigue life calculation estimation equation, what do you write? You write it this way. So it has the stress dominated the high cycle fatigue life component, at the same time the low cycle fatigue life component also. Okay. This is to be okay. This is on, you know, the crack and fracture mechanics. So typically, you know, okay, let me give you a brief overview. This is basically, you know, your stress intensity factor. Okay, I'll not go into really much detail of stress intensity factor, but what they say is if you have crack inside your body, okay, then the life of the component is regulated with respect to you know, delta K, which is delta stress intensity factor. Okay, stress intensity factor K max and stress intensity factor K mean. So it is not really strain or stress, it is stress intensity factor which governs your life in presence of, you know, uh, crack. So now stress intensity factor is basically some constant into sigma. So stress root pi times A. A is your crack length. The A, let's say, you know, if you have this component here, this part here, and if you have this very line crack, then you know this crack length is taken care by A, and sigma is the stress level at the tip. Okay, so and then A is basically a geometry constant which is different for different geometries. Okay, different type of crack geometries also. So so basically a thing to be noted here, that in presence of crack, it is stress intensity factors delta which controls your fatigue life, and not really the stress and strain absolute. Okay, and what you say that a growth of fatigue crack, the rate of crack growth, fatigue crack growth, is this C times, which is again a constant, delta K times to the power n. This is Paris law, if I remember well. Yeah, it's a Paris law. Okay, and one more interesting thing is, you may see that this curve is starting from here. So the rate is very fast, and then this is, you know, more or less constant. So what you get from this equation from Paris law is crack growth rate in this zone, not really tertiary zone or, you know, primary zone here. Okay, so when this happens, it is a kind of catastrophic failure. You cannot do anything. You can only do something here in this zone. Now how it is useful, let's take an example of aircraft wing. Okay, you have certain crack you know, present in the wing. Now you say that, you know, you have to travel a distance from Delhi to Mumbai. Okay, so what you can, you know, for that crack length and for that loading whichever comes on aircraft wing, you may say that, okay, we are here, and when it travels from Delhi to Mumbai, the crack may propagate, okay, only till here. Okay, or say the number of life cycles, fatigue life cycles with that crack is, let's say 10 hours, but you have to travel only for 2 hours. Okay, so what it means is, you can still accommodate to fly with that crack. Okay, I'm just giving an example here. Don't take it in a very, you know, a literal way. Okay, so this is how your the presence of crack and the fatigue life for cracked specimen is taken care. Okay, but one interesting thing which you can see here is, there are certain crack lengths below which it is observed that no matter whatever is the, you know, stress, the crack will not be propagated. Okay, so if you have very small crack present here which is this zone, such that I mean, I should have not used no matter how the stress is. Stress also plays a role, but what you have to focus is, the crack length is so small that your K, I mean the stress intensity, delta of stress intensity factor is within this limit, okay, is below this. If this is the case with combination of crack length and stress, okay, the crack will not propagate, okay, during your life cycle. Okay, so this is all about fatigue. And okay, these are the tools here which are available for, you know, the fatigue life. Uh, so typically FE-safe and ENCODE. Okay, these are the tools for fatigue life estimation. And FGRO and NASGRO, these are for, you know, these are more used for, you know, fracture and basically a residual strength in presence of a crack, or, you know, those those estimations. Okay, so as you see, I have snapshot of FE-safe here. So now see, select an algorithm to be used. Okay, so you see here biaxial strain, you know, you see here maximum shear strain, you know. So all these fatigue criterias you may want to select out of this. Okay, so typically, you know, uh, I don't see Goodman correction, but I know that Goodman corrections and, you know, different mean stress correction are already incorporated here in the algorithms of you know, FE-safe. So FE-safe gives you a flexibility to, you know, choose algorithm which is like max principal, stress or strain, and Goodman, or, you know, you want strain based Brown Miller. Brown Miller is one more way, you know. Brown Miller algorithm, what it says is that cracks, I mean fatigue life happens when, you know, the crack nucleates along the maximum shear plane and then, you know, opened by maximum principal strain, maximum principal stress. So those are, you know, there are multiple algorithms, fatigue life estimation algorithms available. Now again, I'll just quickly take over through this random vibration, you know. So random vibrations are basically the vibrations which have, you know, varying amplitude, varying pattern. Okay, so what you do is random vibrations are, you know, typically uh, expressed in terms of power spectral density. So what power spectral density shows you, you know, is that for a given frequency, how much kind of energy is given to the component in a layman's language. Okay, so at this frequency, because of all the random vibrations, the energy, you know, thrown into the component was very high. But as you go high, as you go towards higher frequency, you know, the energy infusement into the component is not really very high, you know. Okay, and this is something which this is something which is, you know, taken out of your vehicle. The accelerometers are mounted on the vehicle, you know, running on the road. You have different vibrations coming from you know, engines, or, you know, road undulations, terrains. So your accelerometer takes, you know, note of all those vibrations, and then finally using Fourier transform and, you know, filtering frequencies, you get finally this PSD plot. Okay, and that is what you use for your random vibration, and this PSD plot is the input for your random vibration simulation. Okay, now because this random vibration itself is, you know, a statistical parameter, what you say is, what typically you try to do is, you try to, you know, input this power spectral density, and you try to get a, hello, you try to get, you try to get a, you try to get basically a accumulative effect of this power spectral density onto your specimen. So let's say if I have to, let's say if I have to, you know, walk over the frequency, if I have to walk over the frequency, what will happen? My stresses will vary like this. Okay, because it's a wide frequency range, let's say from 0 to 1000 hertz. Okay, I have given input of, you know, PSD, and at different frequency I'm getting stress. So can I take out one stress? Can I take out one stress? No, here one stress, here one stress, here one stress, here. So what they do is, they typically take root mean square value, RMS value of the stress. which is coming out of this analysis. So typically root mean square value, which shows kind of equivalent, equivalent stress value for this random vibration profile is taken. Okay, now interesting thing is, now do you really see I mean, one thing you can do is, that you can really take this root mean square and check with your endurance limit. Okay, I mean, obviously endurance and mean, because this is vibration, this is high cycle fatigue. Okay, okay, because it has multiple number of cycles and the ranges are very small. Okay, the load ranges. So you can take it to your old, if you remember the equation, Baskin's equation we discussed. Okay, so you take this root mean square stress to your Baskin's equation. Okay, you correct for mean and then you calculate your number of cycles. That is one. I mean, that is conservative approach. But because it is random vibration, because the profile is not very certain, what they say is, what they say that it is, it has to be normally distributed. Okay, I mean, there is a possibility that this stress, that stress may not be really this high every time. Okay, this may be, so what you do is, there is one Steinberg 3-band method. What it tries to do is that it says that okay, now a conservative approach is rather not considering RMS, you consider 3 times of RMS to include all type of uncertainties. So you basically don't take only RMS, you take your stress outputs 3 times, so that you cover all entire band. Okay, when you take 3 times of your stress band, you are trying to imitate that your random vibration cycle. Okay, you are taking care all type of uncertainties into that random vibration input. Okay, what if terrain is more severe? What if bumps are more deep? I mean, more of more height, or pots are more deeper. You take kind of all level of uncertainties. But what Steinberg said is that if you take 3 sigma RMS, you are going too much conservative. So why not take 3 sigma? Why not divide it into 3 bands and you take only one time? I mean, you take only RMS to be present for 68% times, then 2 times of RMS stress to be present for 27% times, and 3 sigma, which is worst case, to be present for only 4.33%. Okay, now as you have different amplitude, one amplitude is 1 RMS, second amplitude is 2 times of RMS stress, and third amplitude is 3 times of RMS stress. You get different number of cycles. Okay, for 1 time of RMS, two times of RMS, and 3 times of RMS. You remember minus rule which we did. So that's how for these 3, now you have different number of, total number of cycles is 72, but you have different number of cycles because this is 68% times, this is 21%, 27% times, and this is 4% times. Okay, so for different number of cycles and different cycles to failure at that stress, you get different damage. Okay, you calculate that. When you sum up that damage, the damage should be less than 1. Okay, so that is what your Steinberg approach says. Okay, so guys, this is the last slide where I briefly also have included the fatigue estimation for simple harmonic, or frequency response, or harmonic analysis we say. So typically we say, you might have seen harmonic analysis input, it is in terms of octave. Okay, so they say that they undergo these many number of cycles, or in this time range, they in 4 hours they have completed 4 octaves, or so on. So what's happening in simple harmonic? In simple harmonic, at every hertz, okay, at every hertz you get certain stress. Okay, and number of cycles for that hertz will depend on your sweep time. Okay, if the sweep time is 2 minutes, number of cycles may be different. If the sweep time is higher, number of cycles may be different for that stress. So what we try to do is, here you can take the resolution as small as possible, or if you take resolution very small as 0.1 hertz, the calculation will be very heavy. So what we have taken here is, uh, uh, a kind of resolution to 1 hertz. And that way, what we try to do is we try to calculate the damage, for octaves. Okay, so, or rather damage, you know so for 1 octave, now you have calculated number of cycles in 60 seconds. Okay, in 24 hours, you know that, uh, uh, now for that 24 hours, how much will be the damage. Okay, so what goes in here? Here again, your Baskin's equation goes in. Here again, your minus rule goes in. Okay, what is changing here? Here, only thing what is changing is to, get an idea of how many number of cycles you have to, expose your stress to. Okay, if your sweep time is fast, or if sweep time is, slow, those number of cycles to which you have to expose your, maximum harmonic stress to will vary. Okay, so guys, yeah, that's all about, my webinar today.